Good morning, students. In the Biomolecules chapter, we have discussed in the previous video about the carbohydrates, their classification, and the glucose, their structure, 2D structure, and the different reaction which confirms the structure of glucose, like glucose containing 6 carbon atom, glucose containing aldehyde group, glucose containing 5 hydroxyl group. Next, we discuss about the structure of the D-glucose, how can we arrange the different OH group in the D-glucose. So let's we discuss at first D-glucose. D-glucose. So if during the arrangement of 5 hydroxyl group, so second position hydroxyl group in the second position always keep on the right side, OH second position, and OH C H OH C H and OH. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 and 6. 6. So 1, 2, 3, 4, 5 and 6. OH group at the position 3, if we count number 1, number 2, number 3, number 4, number 5, number 6. So at third position OH group written in the left hand side, and position 5 the OH group written on the right hand side. If we count from top to bottom, so third position, if we count top to bottom 1, 2, 3, 4, 5. So second position OH group written in the right hand side, your right hand side, and third position OH group written in the 1, 2, 3, 1, 2, 3. So third position OH group written in this side. So suppose we count the number here 1, 2, 3, 4, 5 and 6. So at the third position OH group kept in the left hand side, and the second position OH group right hand side. And 1, 2, 3 and 1, 2, 3. 3 OH group right side written in the right side, and second position means 5 OH group also in the right hand side. So in this way we can find out the structure of D-glucose. How many chiral carbon present? So write down the carbon. 1, 2, 3 and 4. So total 4 chiral carbon is 1 chiral carbon, 1, 2, 3 and 4. So total 4 chiral carbon. And how can we find? 2 power n, n is the number of chiral carbon. So 2 into 4, total 16 possible configuration exist. So 16 possible configuration exist in the nature about the D-glucose. So let's we discuss the another topic, 3D forms of glucose after 2D forms. So 3D form of glucose. 3 forms. 3 forms, 1 alpha and 1 beta and 1 cyclic. 3 forms we will discuss. alpha beta cyclic. In fact, alpha beta cyclic form we will discuss. Alpha beta cyclic form. So at first we write the structure of glucose, D-glucose, uh, C, uh, H, and this is the Fisher projection in which we use this type of sign 1, 2, 3, 4, 5 and 6. One, two, three, four, 5 and 6. And as we know, position 1, 2 and 3, the OH present here, and OH, H, OH, OH, H, H and H. So it is the structure of D-glucose. Why it is called D-glucose? Because this OH group is present in the right side. So we will discuss here in the 3D forms of D-glucose. What happened? Here is the pi electron which goes more electronegative oxygen. In that condition, positive charge appears on the carbon. So this lone pair present on this oxygen goes to satisfy this positive charge, and oxygen acquire negative charge by taking pi electrons and get connected with, take this protons. So one cyclic form is formed like this. So oxygen donate the electron pair to the carbon, and negative charge present on the oxygen is satisfied by taking this protons. So the compound form like C, 1, 2, 3, 4 and 5, like this. 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5, 6. CH2. 1, 2, 3, 4, 5 and 6. So the bond formed between first carbon and the fifth carbon means this fifth carbon. Here is the H and here is the OH, again H, position 1, 2, 3 position is OH, and here is the H, OH, OH and H. So total number of chiral carbon is again 1, 2, 3 and 4. 4 again chiral carbon is present. So one this type of cyclic structure form, which is called the alpha form, or it is called the alpha D glucose. Alpha D glucose. So how many chiral carbon present? So total 1, 2, 3, 4 and 5 chiral carbon is present. 1, 2, 3, 4 and 5. So it is the cyclic form, and total 5 chiral carb center is formed. So, and one more structure form if this OH group present in the left side like C, and here is the OH group is right side, here is we kept the OH group in the left side. So H and 2, 3, 4, 5 and 6. So OH, OH, H, OH, H, OH, H, 1, 2, 3, 4, 5 and 6, and H, and this makes a bond with number 5 carbon. So this is 1, this is 2, this is 3, this is 4, this is 5. So it is called the beta form. It is called the beta form. Beta D glucose. Beta D glucose. They are the anomers of each. They are the anomers of each other. They are the anomers of each other. Only the position of OH. If position of OH means only we consider the carbon number 1. The position of OH group is considered for only the carbon number 1. If number 1 carbon OH group present on the right side, this is called the alpha form or alpha D glucose. If the number 1 carbon OH present in the left side, it is called the beta form or beta D glucose. So this is the Fischer projection. It is called the Fischer projection. Fischer projection, in which we symbolize the carbon by like this type of straight chain. So what is anomers? So anomers are the compound in which we consider only the position of OH group at the carbon C1. So let's the representation of alpha form in the cyclic form. So here we discuss the alpha D glucose cyclic form in which 5 chiral carbon center. So at first representation of alpha form. Alpha form, or we call it pyranose form. Pyranose form. Pyranose form. We know the structure of pyranose like this. This is the pyron. This is the pyron. So how can we arrange the alpha D glucose in the cyclic form? So at first we draw the structure of alpha D glucose. So C, OH, H number 1 carbon and 2, 3, 4, 5 and 6, and the bond form between 1 carbon and 5 carbon with O. So here is the H, here is also H, here is the OH, and 1, 2, 3, the third position, OH always in the right side, H, OH and H. In this way you can arrange the structure of glucose. This is the alpha form or alpha D glucose. Alpha D glucose. Alpha D glucose. So the process to form in the Howard projection in the cyclic form. So in the alpha form, right side OH group goes on the down form, and left side of OH group kept in the upper side. So So in the alpha form, right, and left up, right down, left up, right down, left up. So let's we draw the structure. Number 1, 2, 3, 4 like this. So number 1 C, number 1 OH right side, so OH, right down OH. So at first we draw the structure like this. One, 2, 3, 4, 5 and 6. CH2OH. Position 1, position 2, position 3, position 4, position 5 and position 6. So write down. So here will be OH, here will be H. Here also OH and H. And third, left side OH, left up means OH come here, H, and 3 OH and H, and the 5 here will be H and CH2OH. This is known as Haworth projection. Haworth projection. This is known as a Haworth projection. So because this structure resemble with paron, so it is also called the Paranose structure. It is also called the Paranose structure. Paranose structure. So in this way you can arrange the alpha forms as well as beta forms. So if we draw the Haworth projection of alpha form, you will also capable for the draw the structure, Haworth structure of beta form also. So keep in mind, right down, left up means OH group. I mean to say that about the OH group. If OH group right, it goes on down. If OH group is left, it goes on up. So in this way you can arrange the Haworth projection also. So let's we discuss about the fructose. Fructose. Again we discuss the fructose 3 forms. First, open chain like glucose, and next two is the cyclic form, alpha form and beta form like glucose. So it is known as ketohexosis. So we write the ketohexose. Keto means ketone, hex means 6. So CH2OH number 2 double bond. So we use Fischer projection in this way. So 1, 2, 3, 4, 5 and 6. CH2OH. So the third position is OH group and the left hand side. So H, OH, OH, H and H, and 1, 2, 3, 4, 5 and 6 position. So here the cycle form D-fructose. It is the D-fructose example. D-fructose means position of OH group is the right hand side. So most naturally occurring form of this particular ketohexosis. So here the bond pi electron shifted on this particular, so it requires negative charge, and carbon positive charge acquired in that condition. The position 5 OH group, this lone pair goes on the particular carbon, and the OH group, this OH group gives on the oxygen. In that condition, the structure formed like this. So CH2OH number 1 carbon and the number 2 C2OH right side, and 1, 2, 3, 4, 5 and 6 CH2OH. Number 1, 2, 3. So OH group here, OH, H, OH, H, H, and the bond formed O between this and this. So this is called the alpha D fructose. So OH group in the right side, so it is called the alpha D glucose. Similarly, one more structure you can draw, like CH2OH in the left hand side, and CH2OH and CH2OH. 1, 2, 3, 4, 5 and 6. So position 3 OH group in this side, H, OH, H, and bond form O, and between 5 carbon, 2 carbon, number 2 carbon with number 5 carbon. So this is 1, this is 2, this is 3, this is 4, this is 5 carbon. So it is called the beta D fructose. Beta D fructose because OH group in the left hand side. So draw the Haworth structure of this particular. So let's discuss the Haworth structure. Haworth structure is similar to the furan. Furan is a compound like this. Furan. So their Haworth structure is similar to the furan, so it is called as a furanose. CH2OH and OH. This is question 1, 2, 3, 4, 5 and it is the 6, CH2OH. So write down up left. So CH2OH and OH, H, OH, H and H. So it is the alpha D fructofuranose, because it is resembled with furan, so it is known as a furan, and it is a 5-member ring. It is 5-membered ring. So Haworth position of alpha D furanose. By this you can draw the beta D fructofuranose also. So let's discuss the next topic, that is called the reducing sugar or non-reducing sugar. So so students, in the next video we'll discuss the reducing sugar and non-reducing sugar, and that's enough for today. Okay.